Building embodied AI applications. AI systems integrated into physical platforms like robots or IoT devices that interact with the real world requires a combination of hardware, software, and AI expertise. These systems need to perceive their environment, make decisions, and act autonomously or semi-autonomously. Below is a step-by-step guide to building embodied AI applications, tailored for clarity and practicality, while avoiding overly technical jargon unless necessary. 1. Define the application's purpose and requirements. Identify the problem. Determine what the embodied AI will do. Examples include a robot navigating a warehouse to move inventory, a home assistant robot for elderly care, a drone for environmental monitoring. Specify capabilities. Decide on the AI's tasks, such as perception, detecting objects, people or obstacles, decision-making, planning paths or choosing actions, interaction, moving, manipulating objects or communicating, environmental constraints. Consider where the AI will operate, e.g., indoors, outdoors, structured versus unstructured environments. Hardware needs. Will it require cameras, sensors, LiDAR, sonar, actuators, or manipulators? Example: a delivery robot needs to navigate sidewalks, avoid pedestrians, and deliver packages securely. 2. Choose the hardware platform. Select a robot or device. Pick a platform suited to your application. Options include pre-built platforms, Boston Dynamics Spot, Unitree's Go-To, or Raspberry Pi-based robots for prototyping. Custom-built. Design your own robot if the application requires unique hardware, e.g., a specialized gripper for picking fruit. Sensors. Equip the platform with sensors for perception, cameras, RGB, depth. For vision, LiDAR or ultrasonic sensors for mapping and obstacle detection. IMUs, inertial measurement units. For orientation and balance. Actuators. Motors or servos for movement or manipulation. Compute hardware. Ensure sufficient processing power, e.g., NVIDIA Jetson for edge AI, or cloud connectivity for heavy computation. Tip: for prototyping, start with affordable platforms like Turtlebot or a Raspberry Pi robot to test algorithms before scaling to industrial-grade hardware. 3. Develop the perception system. Goal: enable the AI to understand its environment. Techniques: computer vision. Use models like WOV8 or OpenCV for object detection and tracking. SLAM: simultaneous localization and mapping. Implement algorithms like ORB SLAM or RTAB map to map environments and track the robot's position. Sensor fusion: combine data from multiple sensors, e.g., LiDAR plus cameras, using frameworks like ROS, Robot Operating System, to create a robust world model. Tools: OpenCV, TensorFlow, or PyTorch for vision tasks. ROS or ROS2 for sensor integration and communication. Data sources: collect or simulate environmental data, e.g., images, point clouds, to train models. Use datasets like Kitty for autonomous driving or synthetic data from simulators. Example: for a warehouse robot, use a depth camera and LiDAR to detect shelves and obstacles, feeding data into a SLAM algorithm to build a map. 4. Build the decision-making system. Goal: enable the AI to plan and execute actions based on perception data. Approaches: traditional robotics. Use rule-based systems or state machines for predictable tasks, e.g., if obstacle detected, stop and replan path. Reinforcement learning, RL train and RL model, e.g., using stable baselines 3 or DeepMind's DM control, to optimize actions in dynamic environments. Large world models. Leverage emerging large world models, like those from World Labs, that predict physical interactions and plan spatially aware actions. Path planning. Implement algorithms like A** or RRT, rapidly exploring random tree, for navigation, available in libraries like MoveIt or OMPL. Tools: ROS for integrating perception and control. PyTorch or TensorFlow for training RL or deep learning models. Gazebo or Isaac Sim for simulation-based testing. Example: a home assistant robot might use RL to learn how to pick up objects while avoiding fragile items, trained in a simulated environment first. 5. Integrate AI models. Pre-trained models. Use existing models for tasks like object detection, e.g. detect RON2. Speech recognition, e.g. Whisper by OpenAI. Natural language processing for human-robot interaction, e.g. fine-tune a model like Llama or use xAI's API for Grok-based dialogue. Custom models. Train models specific to your application using labeled data or transfer learning. For example, fine-tune a vision model to recognize specific objects in your environment. Train a navigation model using RL in a simulator like NVIDIA's Isaac Sim. Edge versus cloud. Decide whether to run models on-device, edge, for low latency or in the cloud for heavy computation. Edge AI chips like NVIDIA Jetson or Google Coral are ideal for real-time tasks. Tip: use xAI's API. https://xai/API. If you need advanced reasoning or dialogue capabilities for your embodied AI. 6. Implement control and actuation. Goal: translate decisions into physical actions. Control systems. Use PID controllers or Model Predictive Control, MPC, for precise movement, e.g., arm positioning or wheel speed. Frameworks. RS provides nodes for controlling motors, grippers, or wheels. Libraries like PyBullet can simulate and test control strategies. Safety. Implement fail-safes, e.g., emergency stop if an obstacle is too close, and ensure compliance with safety standards for human-robot interaction. Example: a robotic arm might use inverse kinematics, via MoveIt, to pick up an object based on vision input. 7. Test in simulation. Why simulate? Testing in simulation reduces costs and risks before deploying on real hardware. Simulators. Gazebo integrates with ROS for realistic physics and sensor simulation. NVIDIA Isaac Sim supports advanced rendering and AI training. Unity or Unreal Engine, useful for high-fidelity visual environments. Workflow. Build a digital twin of your robot and environment. Test perception, planning, and control algorithms. Use simulated data to train or fine-tune AI models. Tip: transfer learning from simulation to real-world, sim to real, can bridge gaps, but account for differences in sensor noise or physics. Deploy and iterate. Real-world testing. Start in a controlled environment, e.g., a lab or small area. Monitor performance and log data for debugging. Use ROS bags or similar tools to record sensor and action data. Iterate. Refine models based on real-world data. Address edge cases, e.g., poor lighting, unexpected obstacles. Update hardware or software as needed. Scalability. If successful, scale to more complex environments or multiple robots. 9. Leverage existing frameworks and communities. ROS/ROS2. The de facto standard for robotics, offering modules for perception, planning, and control. Open source libraries. OpenCV PCL Point Cloud Library for perception. MoveIt for motion planning. PyTorch, TensorFlow, or Hugging Face for AI models. Communities. Engage with forums like ROS Discourse, Reddit's r/robotics, or X posts tagged with #robotics or #embodied AI for insights and troubleshooting. 10. Consider ethical and practical challenges. Safety. Ensure the AI avoids harm to humans or property, e.g. ISO 10218 for industrial robots. Privacy. If using cameras or microphones, address data privacy concerns. Robustness. Test for failure modes, e.g., sensor failures, unexpected human behavior. Cost. Start small with platforms like Raspberry Pi or Arduino.